Let's assume here we have a solution that contains two volatile components. Now the airspace above the liquid is going to contain gas phase particles from both of these components. We'll represent that as these are some gas phase particles from one of the components, and the other component is also going to have some gas phase particles in the space above the solution. The pressure due to these gas phase particles is the vapor pressure. That due to only component A is a vapor pressure of A. That due to component B is a vapor pressure of component B. So to calculate the pressure above the solution, we're going to apply Raoult's law twice. Once to component A and another time to the second component. All right, in this problem we're told we have so many moles of water and we have so many moles of ethanol. And the first question is, which is the more volatile component? The more volatile component is going to be the one with the higher vapor pressure, which here is the ethanol. As we see that the ethanol has a vapor pressure of 61.2 millimeters of mercury and water is only 23.8. The next question is to calculate the mole fractions of each of these components. So the mole fraction of, let's take water, is going to be the moles of water, which is 2.17 moles over the total moles, which is 2.17 plus 1.39. We chunk this out. We see the mole fraction of water is 0.61, and we're going to add a 0 so that we have the appropriate number of sig figs. We could do the same calculation for ethanol, but we also know that the sum of the mole fractions has to sum to 1, so we can subtract the mole fraction of water from 1 to get the mole fraction of ethanol, which is 0.390. Now these are the mole fractions in the liquid phase. The next step is to look at the gas phase. And to do that, we have to apply Raoult's law. We do that for both of these components. So the vapor pressure of the solution is going to be the vapor pressure due to ethanol plus the vapor pressure due to water. Because again, see, we have particles in the gas phase above the solution of each of these components. So we'll apply Raoult's law twice. So we want the mole fraction of ethanol times the vapor pressure of pure ethanol. And for water, it's going to be the mole fraction of water times the vapor pressure of pure water. Okay, we retrieve the numbers from our calculations. We have 0.390 multiplied by 61.2. That's for ethanol, and for water, its vapor pressure 23.8 millimeters of mercury. Okay, so mathematically, this comes down to be 23.868 millimeters of mercury for ethanol and 14.518 millimeters of mercury for water. We could report our intermediate values if we pay attention to sig figs here. Okay, looking at this number, we see that we could report 3 sig figs for each of these and get the results that the vapor pressure due to ethanol is 23.9, and the vapor pressure due to water is going to be 14.5. We'll go back to our unrounded values to get a total. And this would be 38.386. We can go to the tenths place, so our total pressure is going to be 38.4 millimeters of mercury. This next question is asking us for the mole fraction of ethyl alcohol in the gas phase. And we can relate the mole fraction of ethyl alcohol by the pressure, the vapor pressure of ethyl alcohol over the total pressure. It's going to be 23.868 over 38.386. Again, we go back to the unrounded values, and this would come out to be 0.62179. It's a unitless quantity because it's a mole fraction. Let's look at sig figs. We can go, these were good to the tenths, so this is also, so that's 3 sig figs. So our final mole fraction of ethanol in the vapor phase is 0.622. So let's summarize here. The mole fraction of ethanol in the liquid phase is 0.39. The vapor phase is much enriched in ethanol, the more volatile component. So let's summarize here. The mole fraction of ethanol in the liquid phase calculated to be 0.390, and in the vapor phase 0.622. Therefore, we see that the mole fraction in the gas phase is much higher than that in the liquid phase, or we say the gas phase is enriched in ethanol, which we can remind ourselves is the more volatile component. And this is a very well known and very well exploited result. For example, if we had a pot here of corn whiskey mash that has some amount of alcohol in it, okay, due to fermentation, and we apply a little bit of heat to it, okay, we can increase the number of particles that are in the gas phase, and further we know that the gas phase is going to be enriched in ethanol. So if we allow that vapor phase to continue through the still and condense down, we end up with a product that has a much higher ethanol content.